No?
Did your head shrink?
How about I just end on time and talk faster? Is that better? No. Okay, so I've told you guys many fun facts and strategies for graphing polynomials, right? Basically, the big idea is if you can take the polynomial and you can factor it completely, then you pretty much know you know where the x-intercepts are, and depending on whether they're even or odd, either bounces or crosses, right? We can calculate the value of the function at 0. We just plug in 0, you know. That tells us the y-intercept. And put those things together and add a few other points, then we got a pretty decent picture of the polynomial graph, right? But the next order of business here is to how we're going to graph rational functions. So what's a rational function? Did somebody tell me? So if, let's say, p of x and q of x are polynomials, then f of x equals to p of x over q of x is a rational function. All right. So how do we graph rational functions? All right. So to graph a rational function, what we need to find out. So here's basically a strategy. Number one, factor p of x completely. Number two, factor q of x completely. And number three, collect like factors, right? You can reduce f of x to f reduced of x by canceling factors. Right. I'm getting into the weeds too much here on number three. Let me erase that. It's not wrong. It's just not the main point yet. I'm going to fix that. So we factor p of x completely. We factor q of x completely. And actually resist the urge at the start to cancel terms, all right? Because it's going to be important to understand what that looks like before we cancel terms, right? If we cancel the terms out, then we kind of lose track of the nature of what we canceled, all right? Because, well, there's a new weirdness here that we should confront directly, and so we'll have to talk about that. That's the idea of a hole in the graph, all right? The other sort of more interesting thing here is if q of x is 0, then we could have division by 0, right? And that gives us what are called vertical asymptotes, all right? And so to graph rational functions, we really want to find, like, we still want to find x-intercepts, right? An x-intercept is going to come from what? Let me say it this way. Possible x-intercepts from p of x equals to 0. Possible vertical asymptotes from q of x equals to 0. All right, but here's the rub, but holes in the graph. Muddy analysis a little bit. But we'll figure out how to deal with it. It's not a big deal. I'm just saying I can't just unequivocally say, oh, if p of x is equal to 0, that means it's a vertical. I mean, it is necessarily a an x-intercept. All right. Let me start giving you some examples to sort of expand on what I mean by 3 here. Okay. So, example 1. So example 1, I'll just make completely about the hole in the graph. All right. This is a very silly example. But suppose we had f of x equal to x minus 3 divided by x minus 3. What's the domain of this function? What's that? Domain is 1? Well, I mean, you're saying domain is 1. You mean the range is 1, right? And that's for what? X not equal to what? 3, right? And it's just undefined. So how do we graph an undefined point in the graph? Remember? We put a little circle, so-called a hole in the graph. So the graph of this is just constant. And then when you're at 3, like so. So that's weird, right? But we gotta look out for that. I guess I could add a number 4 here. What's the domain of f? It would be x in the reals such that what? Such that q of x is not equal to 0. So basically the domain of the rational function is everything except for where your denominator is 0. All right? Those places where the denominator is 0 are either going to be a place where there's a hole in the graph, right? Like example 1, the denominator is x minus 3. So the domain is everything except for where x is equal to 3. And this one there's no vertical asymptote for example 1, right? Example 2, if we look at f of x equal to 1 over x minus 3, right? Then what's that look like? Right? So if you think about x equals to 3, that's called the vertical asymptote here because, because the function gets closer and closer to that as you get close to it, but it never quite gets to it either, right? Like we can make a little table of values over here just to gain a sense of perspective. So here's x, right? If we put in like 3.1, if we put in 3.01, if we put in 2.9, if we put in 2.99, what do we get? For 1 over, f of x. Can you run the numbers for me? What's 3.1 minus 3 is what? 0.1? What's 1 over 0.1? 10, right? So the next one is 1 over 0.01. What's 1 over 0.01? That's 100, right? So you can see where it's going. Like if we got 3.001, we get 1,000. If we put 3.0001, I forgot how many O's, but we get either 10,000 or 100,000, depending on how many O's I just said. But we're going to get stupidly large as we approach 3 from the right, right? We're going way, way up there. So but we never actually get to 3, right? We can't plug in 3. Something like this, right? So I don't know, maybe this is 10, you know? Maybe this is 100 on my scale, I don't know. And then on the other side, what happens? You get minus 10, right? And you get minus 100 because 3 minus 2.9, excuse me, 2.9 minus 3 is minus 0.1. 2.99 minus 3 is minus 0.01. So we get minus 10. We get minus 100 on the other side. And so, you know, it should be symmetric, like it should be the same kind of approaching from both sides, right? If I could draw it exactly like I should. Okay? So in this sort of situation, we say f of x goes to infinity as x goes to 3 from the right, right? And we say f of x goes to minus infinity as x goes to 3 from the left. But more generally speaking, if you have a function and you have a point outside of the domain of the function, and the function either goes to plus or minus infinity from either side, then it's said to be a vertical asymptote. All right? So, all right, let's keep looking at more examples. Now this one's going to be a little bit weird. This is also a rational function, all right? But this one's interesting in the sense that it doesn't have any x-intercepts, right? Because x-intercepts come from what? Come from the numerator equal to 0, right? The numerator is 1. Can the numerator be 0? No. The denominator is x squared plus 1. Can x squared plus 1 be 0? No, right? So what's the domain of f? It's everything, the whole real line, right? And so this one, to graph this, pretty much your only strategy is just to plug in some points and just try to think about things, right? A little bit. So let's just make a little table of values to just kind of guide our steps here. We plug in 0, we get what? We get 1. If we plug in plus or minus 1, what do we get? Oh, man. We get 1 over 1 plus 1, right? It's a half. So we get like 0.5 at either plus or minus 1, right? This function is what's called an even function, right? If I calculate f of minus x, it's equal to f of x. Because when we square minus x, we just get x again. X squared, right? Minus x squared is equal to x squared. And this gives us what? Yeah, 0.2, like 1/5, right? And you see what's going to happen, right? As x gets really, really large, we're going to do what? We get closer and closer to 0, right? So this is kind of like a bell. So something like that. we go, y equals f of x. Now, you can tell me some things. Our graph has been made careful enough. You could tell me what the range of f was, right? What's the range of f? What are the possible y values that are attained for this function? 0 not included, right? To 1 included, right? Now this function doesn't have any vertical asymptotes, right? But what it does have is horizontal asymptotes, right? Notice we have horizontal asymptote. Or a of y equals 0 for x going to infinity and x going to minus infinity. See the difference? Horizontal asymptotes concern the x values going to either plus or minus infinity, right? Whereas the vertical asymptotes concern the y values going to plus or minus infinity, right? Very similar idea, but one has to do with the domain, the other one has more to do with the range for a given function. Is there a horizontal asymptote we could have mentioned over here? So these, again, were vertical asymptotes. There's also a horizontal asymptote of what? Y equals to 0 as x goes to plus or minus infinity. We could add that to the last example, couldn't we? See, because it's also happening here, isn't it? So does every rational function have a horizontal asymptote of like 0? Is that what always happens? Like it's happened for 2 of my examples. It didn't happen there, I guess. This is kind of stupid, but this is very stupid, but there is also a horizontal asymptote in example 1. Now that I look at it, horizontal asymptote, y equals 1 as x goes to plus or minus infinity, right? But I think a lot of people would forget to even talk about that, but it's there. So that is a significant difference between horizontal and vertical asymptotes. The horizontal asymptote you can cross. You can even be it. That's allowed. All right? But the vertical asymptote, pretty much we can't cross. Because if we did, well, we would run into troubles with how infinity is defined, basically. And if you actually were the vertical asymptote, it wouldn't be a function, right? Because it would fail the vertical line test.
So you're only finding the horizontal asymptote?
I'm interested in both horizontal and vertical asymptotes because knowing where they are helps me graph rational functions.
So on example 2, the vertical asymptote would be 3.
Yeah, x equals to 3. So a vertical asymptote we can write in the format x equals something. Horizontal asymptote will be y equals something.
Where there's no value.
Right, where there's, yeah, for the vertical asymptotes, it would typically be a point outside the domain of the function. Of course, if we had math majors in here, they might do something like say, well, I'm going to define f of 3 to be 7. You know, I'm just going to add a point right here. Ha! So I can, but I forbid that in this course. So ignoring wiseacres who do stuff like that. Let's go on. All right, so f of x equal to x minus 2 over x squared minus 4. All right, let's try to graph this thing. So take my advice. First of all, I should factor completely the denominator. Right? And so you see we could factor something out, right? Notice that f of x is equal to 1 over x plus 2, right? For x not equal to 2. Right? When x equals to 2, we have the formula is not defined, right? And, well, I mean, I guess technically speaking, I should also say what? And I forgot another term in condition here, what? We also need to have x not equal to minus 2, right? So, all right, so actually, for the points in the domain of the function, that's actually the formula for the function, right? But here's the trouble. If I just write f of x is equal to 1 over x plus 2, you're going to lose track of the original expression, possibly. And you're going to forget that, I mean, unless, you're going to forget it unless you emphasize this over here, right? And that over there is going to do two things. One thing is the sort of thing you can't miss, which is that there's a vertical asymptote at minus 2, right? But the other thing is that there's a hole in the graph at x equals to 2, right? And if I just told you this, I don't think most of us would put a hole in the graph at x equals to 2, right? How would you know it's there if all you had was this formula? So, so here we go. X equals minus 2 is my vertical asymptote. And so this is basically just the 1 over x graph shifted 2 to the left. So we know it looks like this, basically. And at 2, there's a hole. Where is this hole specifically? How do you figure out the y-coordinate of the hole in the graph? You certainly can't plug it into the original formula, because that gives you 0 over 0, right? What you do is you plug it into the reduced formula, and that gives you 1/4. What's the y-intercept here? Plug in 0, right? F of 0 is 1/2. The y-intercept is 1/2. But there you go. We good? All right. Let's do another. You guys tell me, what's the horizontal asymptote for that one? What's that? 0, right? As we go to plus or minus infinity again, right? No, I mean, as x gets really, really large, for x, absolute value of x much, much greater than 0, we find 1 over x plus 2 is going to like 0, basically, because it's like 1 over something huge. What are you asking about a half for? Oh, this is 1 over 2 plus 2. So like f of 2 is, well, I mean, f of, I technically, what I'm trying to say here is I could define a new function, g of x, equal to 1 over x plus 2, for x not equal to minus 2, and like g of 2 is 1/4. Why are you asking me about a half? Excuse me. No. Example 5. F of x equal to x squared minus 9 over x squared minus 16. All right, so we can complete the, factor the numerator. We get what, x minus 3, x plus 3, right? X minus 4, x plus 4. Nothing cancels here, right? There's no, no commonality between the numerator and the denominator. So this is a nice example. It has well, this one has no hole in the graph, right? There's no hole, but it does have two vertical asymptotes, right? We have vertical asymptote x equals to, plus or minus 4, and we have, x-intercept where x equal to plus or minus 3 because of the numerator, right? That's where the function 0. And what about really, really large values of x? What happens? A couple different ways to look at it, all right? We could do long division on this, right? Whenever you have a rational function where the degree of the numerator is equal to the degree of the denominator, you could do long division and, figure out how to rewrite it as like a constant plus a quote-unquote proper rational function. So, or you could do the following trick. I'm fond of this trick. So how do I make 9 turn into 16? If I put minus 16 and I have a minus 9 there to start with, what do I have to do to be fair? Minus 7? Right idea. Put plus 7, right? See, because the original numerator has to match the modified numerator, right? And then, well, that's x squared minus 16 over x squared minus 16, right? Plus 7 over x. So what I'm doing right now, guys, is I'm showing you a trick to just avoid the long division. This is it's an algebra trick I'm fond of. You can take it or leave it, but if you either do my trick or do long division, you'll get 1 plus 7 divided by x squared minus 16, right? Now, fun fact. If the degree of q of x is greater than the degree of p of x, then p of x over q of x goes to 0 as the absolute value of x goes to infinity. Or let me put that in other terms, as x goes to plus or minus infinity. What I'm trying to say is if you have a rational function where the denominator function has a larger degree than the numerator function, eventually it will take over and dominate the expression and force it to go to 0. So like 7 over x squared minus 16. For x really, really large, that is stupidly small, right? It's essentially irrelevant after well, whatever precision you want, right? If you put in 1,000, that thing is like a millionth, right? If you put in a million, that's like 1 over 10 to the 12th or something, So 7 over x squared minus 16 is very, very small for large x. And so what's the horizontal asymptote for this one? Looking at this, right? So if we look at y equals to 1 plus 7 over x squared minus 16, we should be able to see that that is going to go to 1 as x goes to plus or minus infinity. So we have a horizontal asymptote of 1 for this one, in contrast to the other ones where we had 0, right? For most of them, except for example 1. Example 1 was weird. What's the difference between this example and like example 4? Well, example 4, we had a what? We had a first degree in the numerator, we had a second degree in the denominator, so that meant after a while the denominator wins, it forces it to go to 0, right? This one is what you might call an improper rational function, because the degree of the numerator equals to the degree of the denominator, right? Now, if the degree of the numerator was larger than the degree of the denominator, what would happen then? Then interesting stuff happens, stuff that I shouldn't talk about in this course. But you can get things called slant asymptotes, or even like parabolic asymptotes. You can basically get the large-scale behavior of the rational function resembling the polynomial part. Because like generally speaking, if you have p of x over q of x, and you do the long division, what you'll get is a polynomial, right? A polynomial piece plus the remainder over q of x, where the degree of the remainder term is less than the degree of the denominator. So as x goes to plus or minus infinity, what happens to this is this piece goes to 0, and you're just left with a polynomial term. And that could be a linear, it could be a parabolic, it could be a cubic, it could be anything. But to be kind to the students, we don't ask you to graph this, except in the case that this works out to a constant, like example 5. So I stumbled into a slant asymptote example in the other section of pre-calculus, but I already told them I wasn't going to test on it. So by rights, it extends to you guys as well, because it wouldn't go well. Now I really want to talk about them more. Oh, I'm going to stop. Okay, so I think we have all the necessary ingredients to make the graph, right? So I'm going to just put in my asymptotes first. Here's y equals 1. And I've got vertical asymptotes where? Plus or minus 4. Right? And what else do I know? I have x-intercepts, plus or minus 3. What does that mean? It means it goes through 0, right here, and right there, right? Can it go through 0 anywhere else? No. Can it change signs anywhere else? Yes. It can change signs at vertical asymptotes, right? So places where you can change from plus to minus in your graph are either zeros, like, or vertical asymptotes. It could also happen if you had a hole in the graph, and that hole in the graph happened to be on the x-axis. That's another place where it could change signs technically, right? All right. So, and then where do we go from here? How about what happens when we plug in f of 0? That might get us started. What's f of 0? Nine sixteenths, right? Minus 9 over minus 16, the minuses cancel. We get a plus 9/16, which is like about here. Roughly speaking. Let's see here, what else? What if we plug in what's f of, let's see, I feel like I need some more guidance. What's f of 5? If in doubt, plug in more points, right? F of 5 is what? That's 1 plus 7 over 25 minus 16. Using my, snazzy formula right here. Or you could use the original formula if you want. It's 25 minus 9 over 25 minus 16. The point is, it is positive, right? And it's also a number. If you use this, you can see it's a number larger than 1, right? So f of 5 is like up here somewhere. What is 7 over? Sorry, I lost track. 7 over 9 is what? That's, well, it's not quite 1, but it's pretty close to 1, right? So this is almost 2-ish. So it's somewhere in here-ish. What would happen if we plugged in like, oh, and this is an even function, isn't it? Oh, hey, that's very helpful. This is an even function. We can use that to half our work, can't we? I should have been looking for that already, right? If is f of x equal to f of minus x for this one? Look at the formula. You can see that that's true, because if you plug in minus x into that, minus x squared is x squared again, right? So f of x is equal to f of minus x, which means that this graph has to mirror itself over the y-axis, right? And so in other words, there's another point just like that over here, roughly speaking. And what happens if we plug in like f of, I'm curious what happens right in here. Could you figure, what value should I test there? What would f of, so f of 5 was like 1 plus 7 ninths. What's f of 3.5? Hey, no, I'm making this too hard. Let's think about this. Let's be sneakier. Let's think about like what is f of 3.99? Like let's get really, really close to 4, but from the from the left side. What happens to 3.99? Think about putting that formula into here. That would give me 3.99 is like just squared is just a little bit less than 16, right? So 3.99 squared minus 16 is a very small negative number. What happens upstairs? We take 3.99 square. We get, about 16 minus 9, which is 7. So basically, we're getting 7 over a very, very small negative number, which is what? That's a very large negative number. And you could run the calculator. Did you do the calculator, Mary?
I did. It's -86.6.
Minus 86.6, right? And that would only get worse. That would only get worse if we get closer, right? So that's because there's a vertical asymptote there, and it's dropping to minus infinity from the left, right? I mean, correct? So we're going to have something like this, right? That's what this told me. So we're going down like that. And I guess I could have probably figured that out already from what I've graphed so far. And on the other hand, over here, it must be that it's doing this. And then it mirrors. And of course, you guys have graphing calculators, so you can check your work also, right? Disagree? What's so funny? What's so funny?
Like you said, of course you don't have graphing calculators. So I was just like, man, I wish I had a graphing calculator.
Oh, you can borrow a graphing calculator from downstairs if you want. They are free of charge. But I think having a graphing calculator takes all the fun out of it, personally. But anyway. I mean, even if you have a graphing calculator, I still will want you to show your work, right? So like, graphing calculators are great, but they don't pick up holes in the graph very well, and they can also be very misleading when asymptotes are involved, unless you just choose the right kind of scaling. I mean, like zooming out and in and stuff. but they are useful, of course. But anyway, it's an example. Example 6. Suppose we had f of x equal to x squared over, I don't know, x to the 4th minus x cubed, no, x squared. There. Let's graph this thing. So first order business, I got like x squared up top, right? And I can factor out x squared downstairs. So, oh, and I can do better than that, right? And so this one, I can actually cancel the x without getting into trouble because, well, I mean, basically the story is this. When we have a factor upstairs and downstairs, and that factor has a larger degree downstairs, that means that there's a vertical asymptote at the corresponding place where the 0 is. If the degree of the factors match up, that means there's a hole in the graph. If the degree of the numerator is larger, then that means there's a hole in the graph at 0. So, yeah. Yep.
When you began, when you said f of x on the second line there, why is it x instead of x squared on the top?
Oh, man. Thank you. And now I'm everything I just, well, not everything I just said, but some of what I just said. So that's fine. X squared over x squared times x minus 1 times x plus 1, right? So basically, this is just going to have a hole in the graph. At x equals to 0. And notice that this is equal to, 1 over x minus 1 times x plus 1 for x not equal to 0 and x not equal to plus or minus 1, right? So there's a hole in the graph at 0, but where is it? So set x equals to 0 in reduced formula. This is the reduced formula, and that gives me 1 over 0 minus 1 times 0 plus 1. So it's 1. The hole in the graph at 0 is at 1. So there's not a y-intercept. There's a hole in the graph at 0 in this one. And then there's vertical asymptotes at plus or minus 1, right? If we plug in a number larger than 1, what happens? Like try plugging in, say, 2. What do you get? You get 1/3, right? So essentially what's going to happen here is it's positive over here, what happens if we plug in a number like minus 2? Plug in minus 2, you get a minus 3, you get a minus, I think it's also like here. Is that right? And what happens in the middle? Oh, here's a question. Does this ever cross the x-axis? What would it take for this rational function to have an x-intercept? You'd have to be able to get the formula to equal 0, right? But it can't. Its best hope for being 0 is 0, but at 0 it's undefined. So this doesn't ever cross the x-axis. And so that means it has to do this. And also this function, again, is even, so there it is. Wacky. That is not what I was expecting. It's like a double volcano. Cool. It's a what bridge? It does look like a bridge, doesn't it? Yep. Yeah, I'm using the reduced formula where I've canceled the x squared out.
It would look like it would equal 1 over -1 times +1.
Uh-oh. Did I do it wrong? Oh, thank you. -1. Woo! I feel much better about this. Thank you, Dimitri. Your name is not Dimitri. I keep turning you into Dimitri. I had a friend in grad school whose name was Dimitri. He was actually Estonian, and once he told me, he's like, James, I'm a very bad person. I always go to party, and I pretend to be drunk, but I'm not drunk. I just try to make people drink. Like, okay, Dimitri. I wasn't really involved in the party scene at all. But I rented a house with some Europeans, and Dimitri's one of them. I think he wasn't he? I can't remember. Anyway, every once in a while they'd have a party, and it was horrible. I'd be like the one person not drinking, and then they're all like, for some reason they've got honey, it's on the floor, they're walking around it. I don't know, it's just horrible. I just see my security deposit vanishing before my eyes. Just horrible. Horrible. Anyway, I guess COVID has fixed all that, right? Here.
There's an easy trick to avoid all that. Bring your own case of drinks and fill up the bottles with apple juice so they don't notice.
I'm sure no one would notice. But there you go, example 6. But wait a minute, I still owe you guys like 10 more minutes of examples, right? You don't want the weekend to start. I have like -2 minutes. Yeah. All right, I'm going to turn that camera off before somebody tells me a joke I need to edit out.